Going into the details on mechanics of the TIDA-01377 design, for the demo we use a 3-phase EVM case that had two cover parts. One cover was the main cover shown on the left, and the other cover was the terminal block cover that goes on top of the main cover. In the one-coil set implementation, we particularly detect an opening of the terminal block cover. When the terminal block is placed on the main cover and screwed down, it causes a platform on the main cover to descend downwards. On this platform, the target metal is placed. In the default state, the metal is at its closest distance with respect to the sense coil. Once the terminal block has been removed, the platform with the metal ascends, causing distance between the metal and the coil to increase. Once this distance is greater than the switching distance, the output of the LC051 would change, and MC430 would log this as a case tamper event. This video shows a demo of this TIDA-01377 one-coil implementation using this 3-phase case. In this video, we show how the TIDA-01377 TI design could be used to detect when someone tries to open a meter. For this particular demo, we use a one-coil set implementation that will be used to determine when someone has opened terminal block cover. To indicate status, we use two LEDs. The third LED on the left, the orange one, indicates if tampering has occurred sometime since the meter was first started. The next LED on the right, the red one, indicates if there currently is a tamper event occurring, if the case is currently open. The case tamper mechanism is immune to DC magnets. Here we see applying a 1.3 Tesla magnet that is 63.5 millimeters in diameter and 25.4 millimeters in thickness above the portion of the PCB used for sensing the opening of the case. From this test, you see that the yellow LED stays off, which indicates that no tamper event has ever occurred. Now let's see this case tamper mechanism in action. By unscrewing the screw that connects the main cover to the terminal block cover, the distance of the target metal with respect to the sense coil increases until it is above the switching distance of 7.99 millimeters. At that point, it would register this as a tamper attack. Again, since this is immune to DC magnets, if we place the magnet above the sensing circuitry, the LEDs will not turn off because they're immune to this DC magnet. Now that we've seen the one-coil implementation design, let's see how the two-coil implementation can be used to both detect when someone has opened the terminal block cover as well as the main cover of an electricity meter. Going into the mechanics of the case, there are two parts of the case. The first part is the main cover shown here, and the second part is the terminal block cover. On the main cover, there is an elevated area. By pressing on this elevated area, a platform that has metal on the inside of the case would descend downwards. So by placing the terminal block cover on the main cover and screwing down, this would cause the target metal to be its closest with respect to the sense coil. This is used to detect when someone has opened terminal block cover. There is an additional target metal on the corner of the case that is above another sense coil to detect when someone has opened the main cover. To show the status of case tampering, we use two LEDs, where the third LED on the left, the orange one, shows if there has been a tamper event sometime since the meter has first been powered. The next LED on its right, the red one, indicates if there currently is an opening at either the terminal block cover or the main cover. This case tamper detection implementation is immune to DC magnets. Here, a strong 1.3 Tesla magnet is applied over the sensing circuitry of the LC051, and in this test you notice that none of the LEDs turn on because it is immune to DC magnets. Now let's see this two-coil implementation in action. By unscrewing the screw that would cause the terminal block cover to press down on the elevated area, the platform with the target metal would increase its distance with respect to the sense coil. until it's far enough to be registered as a tamper event. This shows how this two-coil implementation can detect when someone has opened the terminal block cover. Next, we screw down the terminal block cover until it is fully closed, which you would see as the red LED turning off. Here we'll test the opening of the main cover. So by opening up the main cover, see that the red LED would turn on, which would indicate that case tampering has occurred. So this specifically detects when the case has been opened. To show that this is immune to DC magnets when a tamper event has occurred, we lifted off the terminal block cover and applied the same strong 1.3 Tesla magnet. From here you see that the LEDs do not turn off because it is immune to DC magnets. So to summarize our findings for case tamper detection, the case is the first line of defense against tampering, so you want to detect when someone opens it. This can be implemented using mechanical or inductive solutions. The inductive implementation is more reliable than mechanical implementation. The solid-state switching of the LC051 removes the failures due to mechanical switching from the push-button implementation. In addition, it is also more difficult to tamper than a mechanical solution. Also, the inductive case tamper detection implementation is immune to DC magnets. The TIDA-01377 TI design showcases how to implement an inductive-based case tamper detection mechanism using the LC051 specifically to detect when someone has opened a terminal block cover. By duty cycling the LC051, we could detect the case tamper event while consuming a low average current consumption, less than 2 to 3 microamps for a sample rate of 1 Hz. This lower average current consumption allows the system to run for a longer amount of time when running off of a battery when there's a blackout. In this design, we detect when the terminal block cover moves up by more than 1 millimeters. This same concept can also be extended to anything else that detects case tampering events, such as gas meters.